Subsets of real numbers and properties of real numbers. First, let's look at our subsets of real numbers.
Let's start with the smallest subset of real numbers. Remember back when you very first learned to count? How'd you count? 1, 2, 3, 4, and so on. Those are called natural numbers. The next subset is called whole numbers. Whole numbers start with 0 and then roll right into natural numbers. 0, 1, 2, 3, 4, and so on. The word itself kind of gives us that hint. The O in whole we could think of as 0.
Then we were introduced to negative numbers. Negative numbers are the opposites of the natural numbers. So for integers, we have the natural numbers, their opposites, the negatives, and 0. What happens when we introduce fractions? What subset of numbers do those belong to? Well, the rational numbers. A rational number is any number that can be written as a ratio of two integers. And what is that known as? A fraction. So in the rational subset of real numbers, we have the natural numbers, the whole numbers, the integers, because we can always write an integer as a fraction. 7 divided by 1, 7 over 1 is a fraction, and so on.
But now you might be asking, what about decimals? What about 0.5?
Well, 0.5 is 1/2. That's a fraction. So yeah, that's a rational number. What about 0.2 repeating? Well, 0.2 repeating can be written as a fraction. So that's a rational number.
How interesting. So a way I can remember rational numbers is they're numbers that can be written as a fraction, a ratio of two integers. Rational, fractional.
But wait a second, are all decimals rational numbers? Well, actually no. But if a decimal ends or it repeats, it is rational because those can be rewritten as fractions. What happens when they don't end and don't repeat?
Well, that's when we get irrational numbers. Not rational, not fractional. So those are numbers like pi or e, which we'll look at more later, or square root of 2, square root of 5, really any root that's not a perfect square root.
Well, that concludes the subsets of real numbers.
I really wish there was a way to remember all these.
Know when it's rational, fractional, or irrational, not fractional.
What do you mean?
Well, you know, like no, but N-O, no. Natural, when, whole, it's, integers, rational, fractional, or irrational, not fractional. Know when it's rational or irrational.
I like it.
So those are the subsets of real numbers. But then we have this little strip on the side. What's that for?
Well, a complex number is made up of both real and imaginary numbers.
And an imaginary number is when we try and take the square root or even root of a negative number. We'll get into that later in the year.
Let's practice. State the smallest subset of real numbers that best fits each example. This first one, the amount of money to buy a phone. Well, I want the new iPhone. That's about $1,000.
Yes, plus tax, therefore decimal.
Decimal, fractional, rational.
Yeah, why isn't it irrational though? Decimal.
Well, we'd end at the hundreds place.
Okay, so it terminates, so rational. Next example.
Number of pencils needed for the math class.
I say infinity.
We're gonna need a lot of pencils. You'll at least need some.
Yes, so natural.
Take a moment to try the next 4.
Let's see how you did. Area of a large versus extra large pizza. It's always important to check that price per square inch.
She really does.
Well, pizza, area of a circle, pi r squared. Pi is irrational, so it is irrational. Next one, cookies left at the end of the week. Well,
I'd eat them all, so there would be 0 left.
Okay, whole numbers.
The sum of 7 root 2 and root 32. Well, we gotta simplify that root 32 first. Largest perfect square that goes into 32 is 16. So root 32 is really root 16 times root 2. The square root of 16 is 4. So we have 4 root 2 plus 7 root 2. Add their coefficients. That's 11 root 2. Oh, looks like it's still irrational. Then I bet this next one's irrational as well, because I got 3 root 36 and root 25. If I add those together, wait, root 36, that's 6. So 3 times 6, that's 18, plus root 25 is 5. 18 plus 5, 23. Oh my goodness, it's natural.
What would have happened if that 3 had been negative?
Well, then I would have negative 3 times root 36, so 6. So negative 18 plus root 25, which is 5. I'm going to get negative 13, so I get an integer. Wow, so just because it has a radical in it does not mean it's automatically irrational.
Properties of real numbers. Given A, B, C, and D represent elements of the real number system, closure property says that if we add two real numbers, the answer will be real. For example, 2 plus 3 equals 5. Likewise, for multiplication, A times B is also a real number.
Identity property of addition. A plus what equals A? Well, A plus 0 equals A. So if A were 2, 2 plus 0 equals 2. That's true. Identity property of multiplication. A times what equals A? Well, A times 1 equals A, just like 2 times 1 equals 2.
Identity property, I think about it like, what do you do to get back what you started with? What's your identity?
Inverse property of addition. A plus blank equals 0. Well, to get 0, I would add its opposite. A plus negative A equals 0. So 2 plus negative 2 equals 0. That's true. Inverse property of multiplication. A times what equals 1? Well, A times its reciprocal equals 1. So A times 1 divided by A equals 1. 2 times 1 divided by 2? Yep, that equals 1.
Ready to drive? Yeah, let's go ahead and commute. When we commute, we move from one position to another. And that's what commutative property of addition and multiplication are. A plus B equals B plus A. Well, is that true? Well, let's think about it. 3 plus 4 equals 4 plus 3. Yep, 7 and 7. Same thing with multiplication. How about associative property? Well, associative property means you have an association designated. But we can change that association if it's addition or multiplication. So you'll see we have A plus B in parentheses plus C. Now, does the value change if we change the association and have A plus parentheses B plus C? No, it's all the same. Let's check. Let's keep the numbers easy. 1 plus 2 plus 3. 1 plus 2 is 3 plus 3 is 6, or 1 plus 2 plus 3, well, that'd be 1 plus 5. 1 plus 5 is 6. The associative property holds for addition. The same idea is shown with multiplication. A times B times C is equivalent to A times B times C. Doesn't matter what order you multiply in. The values are equal.
Last, we have the distributive property. Now, this may be one you've seen before. A times parentheses B plus C plus D is the same as A times all three of those terms. So, A times B plus A times C plus A times D.
Let's practice the properties of real numbers. Read each example and determine which property is demonstrated. Be sure and say of addition or of multiplication as it applies.
Let's see how you did. On the first example, it appears just the association changes. First, it's around n plus n, and then the association changes to n plus q. The order didn't switch, so it's not commutative. Associative property of addition. Be sure you write out the whole name.
And next, we see a product and it equals 1. So that's kind of a good clue for me. How did we undo and get 1 from 2/5? We multiplied by the reciprocal. Inverse property of multiplication.
C, negative 10 plus 4 equals 4 plus negative 10. That's just the order. Commutative property of addition.
Q times 1 equals Q. Well, I got back what I started with, so I think that's identity property of multiplication. Okay, the last one I think could have fooled anybody. We see those parentheses and we think association, but what's in the parentheses? S plus T. Did that change? S plus T, S plus T. It didn't change. What did change? Well, the R was in front, multiplied to the S plus T, and then it moved to the back. It commuted to the back. So now it's S plus T times the R. So commutative property of multiplication.
I can't look at you.